Now let's get into the fun stuff. This claim's gonna sound weird, but actually, let's start here. Did you guys go over like division rules in elementary school, like little tricks to determine like if a number was even or divisible by 4 or divisible by 3 and stuff like that?
Yes. In fact, I teach this now.
Oh, there we go, Alex. So what's the division rule for 3?
So the sum of the terms is divisible by 3, and you can do this recursively.
Yeah, sum of the digits, right? So here's the claim we're talking about here. And for reasons that we'll talk about in a second, I'm only going to do 4-digit numbers, but this works for everything. All 4-digit numbers n are such that n is divisible by 3 if and only if the sum of the digits of n is divisible by 3. So this might sound confusing. What this means, right, is someone give me a great 3-digit number. I'm sorry, a great
4-digit number?
Any great number divisible by 3. I'm going to say, how about 135? So 135 is divisible by 3, because if you do the math, it's going to equal 3 times what? It's going to be 3 times 45, right? Because 45 times 3, 15, 3 times 4 is 12, plus 1, 135. So 135 is certainly divisible by 3. And then also notice that if you take the digits of 135 and add them together, 1 plus 3 plus 5 equals 9. And 3 also divides 9. So the claim is that n is divisible by 3 if and only if the sum of the digits of n is divisible by 3. And we can do this for anything, right? I mean, just look at 15, right? 15 is clearly divisible by 3, right? 3 times 5 equals 1 plus 5, which equals 6. 6 divisible by 3. 21, that's going to equal 2 plus 1, which straight up equals 3, clearly divisible by 3. This always works. It's kind of weird, right? So, before we start talking about that, let's list one fact that we're going to need. And this is a fact that you're going to prove in the homework to show up this proof. And here's the fact. I'll just write it mathematically. For all A and Z, for all B and Z, and for all C and Z, A divide B and A divides C implies A divides B plus C. Is a fact. All we're saying here, all this means is if A divides B and A divides C, then A will divide B plus C. And just to do some examples of that to show it doesn't make sense. If A was like 5, for example, note 5 divides 10, and 5 divides 35, and then clearly 5 also divides 10 plus 35, which equals 45. If it divides both, it'll divide the sum. right? Like 7 divides 21, and 7 divides 28, and then 7 will divide 21 plus 28, which equals 49. These are examples. These don't prove it works. We prove it works in the homework. But the point is, I think this is easy enough to think about. Like if 7 evenly goes into 21 and 7 evenly goes into 28, you would think it would kind of evenly go into like 21 with 28 stacked on, right? That makes sense to me. And hopefully it makes sense to you by Friday. So any questions on what this means? Cool.
Just a quick clarification. So we can use this as like a given fact, or do we have to prove this as part of the proof for the homework?
The homework is going to be exactly to prove this.
Oh, okay, cool.
Yeah, but for now we're going to use it as a fact. Just because we don't have time to prove everything in class, sadly. I want to do some more interesting things. So yeah, so this is what we proved in homework, but for now we can use it as a nice red fact. So what's the first thing we do when proving anything?
Formally state it.
Formalize it, right? Let's try to formally and really be clear on what we're talking about here. So formally, this is going to be a little weird because A is divisible by 3. That's easy enough, right? That just means 3 divides n. But if only if the sum of the digits of n is divisible by 3, that's a little weird to formalize. Let's notice this, right? You take any 4-digit number. So for example, if you take 2020, what a year. What's 2020 saying? Like if we go back to elementary school, right? We're talking about like what our number system actually means. What's 2020? Like what's this 0 refer to?
0 ones.
Yeah. This means we have 0 ones. This 2 here means we have 2
tens.
The 0 here means we have 0 100s or 10 squares. And this 2 here means we have 2 thousands or 10 cubes. So 2000 equals 0 times 1 plus 2 times 10 plus 0 times 10 squared plus 2 times 10 cubed.
Well, if you're going to write it that way, maybe you should write it as 10 to the 0 and 10 to the 1.
Not a bad way to look at it. Yeah. So, just to give you another example, 1967. I don't know why. I have no idea what happened that year. But that would be 7 ones, so 7 times 10 to the 0, plus 6 tens, plus 9 hundreds, plus 1 thousands. So the point is, this is what digits really mean. It can be written this way. So the first thing I'll do is I'm just going to define a set here. I should do it in blue for some reason. Let's define a set S, which is the set of 4-digit numbers. So let's define S to be the set of all numbers that can be written like this. A0 times 10 to the 0 plus A1 times 10 to the 1 plus A2 times 10 squared plus A3 times 10 cubed, such that they're mowing the lawn very loudly in my apartment complex, apparently. Good timing. Such that A1, A2, and A3, what are the restrictions on the digits?
They have to be real numbers.
They have to be
Natural
real numbers?
less than
What?
10. Natural numbers less than 10. Greater.
Exactly. They have to be
Yeah.
specifically
Oh, yeah.
0, 1, 2, 3, out to 9. Because you can't have like, the way we define our number system at least, you can't have like the square root of 2 pi, the square root of 2 pi 0e or something like that. You know what I mean? Or even like 1.2 or something. You need whole numbers, specifically less than 9. Any questions on this definition right here? And by the way, this is going to be the exact same thing as all the numbers between 0 and 1,000, or sorry, 0 and 10,000 or 9,999. But it's better for us to look at it this way for our proof. So these are all the 4-digit numbers, because they're all the possible numbers that could be written like this, where you have 4 digits, where the digits are A0, A1, A2, and A3.
Small comment is that should we, like, I don't think it actually in practice matters for the negative 4-digit numbers, but should we make some mention for the negatives in our proof?
Yeah.
Or
No, we're just gonna forget about those for a second. But this idea is gonna work for everything, and so if you wanted to extend it, you totally could. But for simplicity's sake, we're just gonna keep it like this for now. Good. I mean, you would need to make all of these negative, but so it would be between 0, -1, -2, as -9 for all of these. That would work. But yeah, see what you're saying? Let's just not worry about that for now. So that was good. So first things first, let's write it formally, right? And formally, the way you can write all 4-digit numbers n are such that n is divisible by 3 if and only if the sum of the digits of n is divisible by 3. Formally what you're doing there, you're saying that for all 4-digit n, and s is exactly defined as all the 4-digit numbers. So you're saying for all n and s, so we got this taken care of. N is divisible by 3, so 3 divides n. If and only if, what's if and only if?
Biconditional.
Biconditional, perfect order, so it goes both directions. If and only if there exists A0, A1, A2, A3, and 0, 1 to 9, and this set of whole numbers here, such that n equals A0 times 10 to the 0 plus A1 times 10 to the 1 plus A2 times 10 squared plus A3 times 10 cubed, where this happens, and 3 divides the sum of the digits. So all this right side is saying is that if you take like kind of the 4-digit number expansion or the 4-digit number way to write n, which you know you can do because n's in s, so this has to exist. If you take that, 3 will divide the sum of the digits. So this is the formal way of saying this. So if we can prove this, we do prove what we're saying here, our division rule, that you can tell if a number is divisible by 3 simply by just adding the digits together and seeing if it's divisible by 3. For a 4-digit number at least, but you'll see this works for everything. So any questions on what we're doing here? Good, okay. So let's do it.